All right, welcome to our second unit on history of the atom. Depending on your state, this may or may not be required by your state standards. However, I think it is helpful for us, especially as teachers, to understand where knowledge comes from. The things that we take for granted, that we have atoms and they have protons, neutrons, and electrons in them. Things you learned like in middle school, possibly even elementary school, that seem so obvious, it's helpful for us to go back in time and see how they got to these ideas. And it starts all the way back with the Greeks. And so it begins with a Greek philosopher by the name of Democritus. And by his bust here, he seems to be like a jolly kind of fellow. And so about 450 BC, the Greeks decided to do a thought experiment. What would happen if you took a piece of something, in this case, let's say aluminum, and we cut it in half? And then we took that half and we cut it in half again. And so on and so on and so on. Would you ever stop? Most of the Greek philosophers said no, that it would go forever. That you would just get smaller and smaller and smaller pieces of aluminum forever. Democritus, on the other hand, said no. We would eventually reach the smallest particle of aluminum. We would finally reach the smallest thing, which he called atomos. The A in the front there means not. Tomos means cut or to cut. And so atomos means to not cut. You can't cut it any further. You can't go any further. That's as far as you can go. Now, unfortunately for Democritus, his idea was not accepted because, think about it. If a piece of paper was made up of a bunch of small little tiny particles, why is it not like a handful of sand? What holds them together? What's going on? And so Democritus' ideas were lost or dismissed. They apparently were rediscovered during the Renaissance. His writings were, because that name atomos or atom stuck. And so everything would sit there kind of undone until really the first person to really make a big step is John Dalton in the 1810s. But prior to that, there were some big ideas that arose in the 1700s. The first one started with Antoine Lavoisier, who is considered the father of modern chemistry. Unfortunately, he lost his head during the French Revolution at the age of 30. He was young and already considered the father of chemistry by that point in time. And so Antoine Lavoisier was able to do experiments. And he was able to determine what we call the law of conservation of mass, that in a chemical reaction, even when it looks like mass is lost, like when you burn something, he was able to trap the gases and weigh them too and showed that the masses remained the same, that what you started with is what you end with. And that was an important piece. And then a gentleman by the name of Joseph Proust, British, he was one who figured out the law of definite proportion, saying that when you have a compound like water, it's always going to be 2 hydrogens, 1 oxygen. Always. And it's always going to be the same percentages or same ratio all the time. So in the 1810s, Dalton was able to take his own observations plus these and write what he called the atomic theory of matter. And so he's the first person to kind of take all of this and consolidate it into one idea. Democritus' idea of the atom, that each element is made of small particles called atoms. He then went a step further and said, all atoms of an element are identical, but different from all other elements, saying that all carbon atoms are the same, but they're different from all the oxygen atoms, which are all different than the iron atoms. And so he was able to make that distinction. What's amazing to me is that apart from the idea of isotopes, and they didn't even know what neutrons were at this point in time, like carbon-12 versus carbon-14, he's correct that atoms, they do this. And then he took Lavoisier's idea and applied it here as well, that atoms are neither created nor destroyed in a chemical reaction, that they happen on an atomic level, and that compounds are made of atoms in relative numbers and types. Once again, that if you have 2 hydrogens and 1 oxygen, that's water. But if you change the ratio and you have 2 hydrogens and 2 oxygens, that's hydrogen peroxide, something completely different. And so that was Dalton's contribution. So that's 1810s. We get this idea of an atom, but we still don't know what makes up atoms. And so that comes later. So during this time period, people were exploring electricity, specifically static electricity. And they're realizing that there has to do something with the atom, something with the stuff that makes up matter is creating electricity. And we got Benjamin Franklin and his famous experiment with the kite, but he did lots of other experiments with electricity, and so they're getting all these ideas. And so by the late 1800s, scientists are experimenting with what's called a cathode ray tube. And J.J. Thomson was able to take this cathode ray tube, which is abbreviated CRT, and if you're older like me, you'll know that those old big TVs and the old big monitors before we got flat screens were called CRT monitors or CRT TVs because they used cathode ray tubes. And so in a cathode ray tube, you've got several components. So we have this, what they call the electron gun in this picture is the cathode. And it would send out a ray, or what they called a ray, a stream of something. And it's bent by magnets. And then you could get it to hit a screen, and you can see where it was hitting. So Thomson was able to prove that this ray here was in fact a stream of negative particles coming off of this cathode. And because it was related to electricity, he just decided to call them electrons. And so J.J. Thomson is credited with discovering the electron. And he was also able to determine the charge to mass ratio of those electrons, which is quite a good achievement. So that's late 1800s, so now we get to early 1900s with Robert Millikan. And so Millikan comes along and he just does this. There's no way to describe this experiment other than ingenious and brilliant. So he takes small drops of oil, and I mean like aerosol small, and he somehow puts a charge on them, and he drops them through a hole between two plates. And one of the plates is negatively charged, one of the plates is positively charged. And he adjusts the electric field, because you remember, like charges repel, opposite charges attract, so he's able to adjust those forces on this little charged droplet of oil until it levitates in between the plates. And by doing this, he's able to get his data along with Thomson's ratio that Thomson had, and he's able to determine the charge and mass of the electron. I mean, it's amazing, especially when you're talking about something that is this small. That the mass of an electron is 9.11 times 10 to the negative 28 grams. Okay, so think again, a gram is about the weight of a paperclip. And so take that gram, weight of a paperclip, put 27 zeros in it, and then a 9. 28 decimal places later, you get to a number. Incredibly small. And it would take 7 times 10 to the 23rd electrons to equal the mass of 1 grain of sand. That's how incredibly small these things are, that he was able to figure out their charge and their mass, which is quite remarkable. So moving on, we get to Lord Rutherford. Now, Lord Rutherford's the one who's credited with this, but it was actually members of his research team that were doing the work. And so they're shooting alpha particles, which are the nucleus of a helium atom. It's 2 neutrons and 2 protons. And they're shooting them at thin sheets of gold foil. And they expected to get uniform results, but what they found is that some of them went through, but others were deflected, and others were bounced back. I mean, this was crazy. Rutherford described it as like shooting a cannonball at tissue paper and having the cannonball bounce back. Like, it just didn't make any sense to them. And so Rutherford went on to theorize that this had to be caused by something with a positive charge, because alpha particles have positive charge. And a positive charge would deflect or repel another positive charge. And that it wasn't just simply a collision, but it was also a repulsion going on here. And so he's able to figure that out, that there must be a solid nucleus in the center. Now, once again, to us, that's common sense because that's what we've always been taught. But prior to this, you have to understand that the primary view of an atom is what they call plum pudding. And pudding is just a British term for a cake. So think of like a chocolate chip cookie would be a good American reference here. So just like in a chocolate chip cookie, you have the cookie and then you have chips. And so the idea was that the positive part of the nucleus, or the positive part of the atom, was just kind of the matrix, that the cookie part, and that the electrons were just like chips embedded within the positive part of the atom. Now, that was not very helpful. So Rutherford's theory was the opposite, that the positive charges were actually consolidated in the center of the atom. And not only was this atom, all the positive charges consolidated in the center of the nucleus is ridiculously small. If you were to take an atom and blow it up to the size of like an arena, think where your favorite sports team plays, like your favorite basketball team. If you blow up an atom to the size, a carbon atom, to the size of that arena, the nucleus, the solid part of the atom, is literally the size of a dime sitting in the middle of the court. And then the 6 electrons reach the size of FTR's I on the dime. And so atoms are in fact primarily empty space, with electrons zooming around inside the arena, and yet they are solid and we don't fall through things. It's mind-boggling. All right, so other key contributions came after. The neutron was discovered in 1932 by James Chadwick. And in 1913, Niels Bohr created a model of the atom that you're probably familiar with, the idea that you have electrons orbiting in electron levels surrounding the nucleus. And that's called the Bohr Model. And so that's how we get to kind of the basic atom model that you learned in middle school and maybe in physical science, or maybe you taught before, that we have a nucleus with protons and neutrons in it, and we have electrons going around in pretty little energy levels. We will disrupt this model in our next unit on quantum mechanics, but for now, this is a good model. It works. And so we'll carry on from there.